Hello, and thank you for tuning into Broadway's Fundamentals of a Load Measuring System. My name is Elliot Van Laere, and I am the product specialist here at Broadweigh. If you have any questions, please feel free to send them in, and we will answer them at the end of the session during the Q&As. We also have a guest today after the presentation, Simon Lawrence from the Rigging Co, and we'll be discussing the use of load cells on the 1975 tour. So now I'd like to introduce you to Tom Lilly. Tom is an application engineer for Broadweigh and Mantracore and has been with the company for over 7 years. Tom has gained an engineering degree and also has been a rigger since the mid-1990s, applying his skills to mostly theatre and outdoor staging. So I now hand you over to Tom.
Oh, thank you for that, Elliot. Okay, let's make a start then. So I think when you're talking about load cells, we have to think about what we're actually measuring. So there's mass and there's weight. Mass is the amount of matter that something has. That's measured in kilograms, which is one of the 7 SI base units that all other units of measurement are defined from. In real life, to my mind, mass isn't actually really that important. It's the force due to gravity that's acting on it that is the important thing. Also, then the way that that force interacts with all the rigging components in the system. Weight should technically be expressed in terms of newtons or possibly kilograms force. However, most lifting equipment is marked with a safe working load limit in units of mass such as kilograms or tons. A very easy approximate conversion between mass and weight is to multiply the mass in kilograms by 10 to give the weight in newtons. And for mass and weight, you need different measuring devices. So the comparative sort of measuring device is things like the balance scales. And as I say, that's to measure mass. And that you get the same results on the moon or here because you're comparing two masses. So you've got a mass of 5 kilos on one side, and so you put 5 kilos worth of weights on the other, and you get that. So wherever you are, there's a bit of gravitational variation around the world, you'll get the same result. A theatrical counterweight system works on that same principle. Another mass measuring technique, which is very accurate, is to simply count the number of atoms of each element in the object and then multiply by the atomic mass. It's very accurate, but not really very practical in everyday life. Another method of measuring weight is deformation. So this is things like spring scales, like a bathroom scale, or load cells. This takes advantage of the fact that certain materials respond in a linear way to a change in weight. So if a spring extends 50 mil with 50 kilos on it, it will extend 100 mil with 100 kilos on it. Today, we're only going to look in detail at the deformation type because that's how load cells work. For a deformation type of measuring device, we require a spring element. That's also known as a flexure. That can be as simple as just a spring with a nice linear reaction to an increasing force. Most metals have a range in which they will extend in a linear way to an increasing force as well, like a spring within its elastic limit. Solid lumps of metal, which actually take decent amounts of load that would be useful, don't deform as much as a spring. They do deform in a similar way to the graph here on the right. This is a stress-strain curve, which shows the extension effects on sample of metal as the force is increased. On the vertical axis, we've got stress, which is the force per unit area. On the horizontal axis, we've got the strain, which is the extension relative to the original length. Up to the elastic limit, which is where that dotted line is the linear section of this stress strain curve. So this is where it's responding in a regular, repeatable way. And the material's conforming to Hooke's law, and it will return to its original length when the load's removed. Once it reaches the yield point, that little sort of blip by the elastic limit, it's permanently deformed. In the same way as a spring will deform when it's stretched beyond its elastic limit as well. At the top there, we've got the ultimate tensile strength. So that's where the material can no longer support the load applied. This is the point that most safety factors are based on. And you can see it's also already well beyond the point of permanent damage to the material. And right at the end there, we have the fracture point. And that's just completely gone then. So now we need to measure that extension. So we know that the extension is a nice linear thing in the right place. Historically, the easy method would be with a spring type measuring device. So in this picture, there's the dial. You could use a ruler just to measure this. This is the little increments on the ruler or dial show you the resolution. So it's how small you can read the result. With a load cell, you can't actually physically, or it's very difficult to physically measure the deformation or extension of that material under the load. So we use strain gauges. Strain gauges are they're a thin meandering pattern of wire that takes advantage of the fact that metal changes resistance when it's placed under strain. As the metal extends and stretches, the resistance increases. As it gets shorter, the resistance decreases. To increase the effect of the strain in the load-bearing material, we can make use of stress concentrators, which make sure that the areas of greatest strain are where we want them to be. We can see in the finite element analysis of a shackle pin there that where the best places for the strain gauges to be placed are. So where those red areas on the sides there. But this is still a really small change in resistance, so it's difficult to measure and see as a real thing. So we need to have a Wheatstone bridge. So Wheatstone bridges were popularized by Charles Wheatstone in the mid-18th century. They're essentially a pair of voltage dividers that will give a zero output when the whole bridge is balanced. So you put a excitation voltage in on the VX, top and bottom, and you take a output voltage from the VO to the left and the right. If all of the strain gauges or resistors are the same resistance, then VO will be zero. As soon as one of those legs changes resistance, it will pull the voltage on that side out, and then you'll get a reading between the VO. Where are we now? So then, if you're when you've got these in a load cell, you need to be able to put them in a sensible manner. If you see the two images of the load cell on the right, the left-hand one has all the strain gauges pointing in the same way, in the same direction. If you loaded that up, all of the resistances would change in almost exactly the same way. And so you'd still get the same zero output on VO. If you see the image to the right, two of the strain gauges are pointing horizontally. So that means that the top two, the resistance will increase as you increase the load, and the bottom two, the resistance will decrease. You put those on opposite sides of the Wheatstone bridge, and you start to get another amplified output on the VO. But this is still very abstract. The output from the bridge is usually expressed in terms of millivolts per volt. So millivolts output compared to the voltage input. So we now need to change this into something more useful again. Signal conditioning is what you'd use for this. And this is basically a way of cleaning up the signal and making it into something more useful. This will also be the point at which calibration will occur, so we can have the right amount of, the right output for any given input. To calibrate a perfectly linear spring, we'd measure the extension at zero load, then measure the extension at full load. from this, we can work out the load per unit extension. To give an example, if you think about using a spring balance to measure 5,000 kilograms, if full scale resulted in an extension of 100 mil, 1 mil would show 50 kilograms. It would be very difficult to take a reading much lower than 50 kilograms, maybe 25 kilograms. And so this again is the resolution of the measuring device. Similarly, if you wanted 1 mil deflection per kilogram, then you would have 5,000 mil deflection at 5 tons. I think this demonstrates the benefit of matching your load cell to the load that you're measuring, and also the reason that the accuracy at lower levels won't be as good relative to the maximum load that you can measure. Load cells work in a very similar manner, although with digital technology, it's also possible to do multi-point calibration. So this will help get rid of any non-linearity in the load cell. We generally find that our pins are pretty linear. We like to do multi-point calibration, still adjust to make them even better. The area that generally seems to be sort of worst relatively is towards the lower end of the scale. So we put in extra calibration points at the lower end. Yeah, for multi-point calibration, we apply various known loads and measure the millivolt per volt output. That data then gets used to apply gain and offset to the various points on the curve. The graph on the right there shows an exaggerated response curve and the corresponding readings. The green dotted line is the ideal linear response. You can see that at a reading of 0.9 millivolts per volt, if it were a linear response, you'd get a reading of probably around about 1,500 kilos, rather than the 1,000 kilos that we've actually measured there. So this is where multi-point calibration would really help. As I say, that's massively exaggerated from real life. You'd be looking much closer than that in reality, usually. Once you've done the calibration, it's also obviously very good practice to do a calibration check to make sure that you've applied the correct calibration points and you're getting the results that you're expecting. Another thing to bear in mind is that if load cells are loaded differently in practice than when they were calibrated, they will give different results. So if you haven't got the bow and the pin perfectly in line and it's all out of alignment, or your bobbin's off to one side or another, you're going to start to skew those readings. So getting everything in perfect alignment will get you the best results. It's not to say you're going to get horrific results if you haven't made it perfect, but the best results come from getting everything perfectly aligned. So the output from the signal conditioner needs to get to some form of display. And there are probably 3 main transmission methods. The first one being analog wired. So this would use a linear 0 to 10 volt or 4 to 20 milliamp output. There'd be a single cable run per load cell to the display. They are quite handy for putting into chain hoist PLCs. So yeah, if you've just got a little run from your load cell straight into the PLC, that's not too bad a thing then. The 4 to 20 milliamp has much better noise immunity over longer distances than the 0 to 10 volt. Downsides really are that for multiple devices, you've got you can have lots of cables, so you've got a cable run for every single one. Plus side is the simplicity of the electronics means that it can be a very popular choice in safety critical systems. Digital wired also uses cable, but with a digital signal. This is less susceptible to interference than analog, generally because error checking should be in use in any decent system, and that should mean that any data that's corrupted due to interference will be ignored. If you lose a connection, if there's a break in the line of any of these sort of spurs, then everything downstream of that will be lost. So that's a big negative there. It can be lots of fun putting in wiring everywhere, but yeah. Finally, wireless. So wireless uses the air as its transmission method. Most people would use a digital signal on this, and again, this should also have error checking in use. Depending on the transmission frequency used and the local conditions, it can have problems communicating, but you'll usually still get some data through. Broadweigh wireless allows for multiple consumers of the data with minimal extra setup, and we use a completely proprietary system for our standards 2.4 gigahertz system, or we also use other current technologies such as Bluetooth for one of our other systems. Not having any wiring and cabling means it's much easier to install without affecting anyone else, and change a system if you change your mind and want to measure another part. Also with Broadweigh, extra transmitters and receivers can be added very easily. Now we want to display the data, and it's making sure that you've got that data available to you in the way that works best for you and the application. Some applications only need a simple handheld display, so for one person can take a reading of or share it around. Others need to be seen from a long distance with a large display or big screens. Sometimes the data might need to be seen and logged, so a PC can do both of those, to display and log. You could also want to display it all the way around the world. So you might need to have some sort of cloud system that takes the data and puts it onto a platform. So we've got a system sensor space that would allow anyone with the right sign-in details to sign in from around the world and view the data and be able to give advice or help on anything that you're doing. It also can trigger alarms and such like. Then you want to use that data. So the simplest way is to live monitor the data. So you've got someone watching all the data as it's happening, and you'd manually take a decision to stop doing something if there were overloads or an imbalance that you're looking for. You could also trigger audible or visible warnings to let people know about overloads occurring. So sirens going off to let everyone know you've got to stop. You could have an EStop to automatically stop a lift. So as soon as an overload's occurred, a dangerous overload's occurred, just the whole system stops and you need to go and sort it out to make it come right. You can also use that data to analyze things afterwards. So if you were monitoring an area list or something and you're sampling at 200 samples a second, you're not going to be able to see what's going on while it's happening. So if you're logging that data, you can then take it and put it in a CSV or something afterwards, see what happened. Similarly, if you've left a stage overnight and it's been blustered by winds and things, you might want to see what happened overnight. You're not actually sat there necessarily watching it the whole time. You can come back in the morning, check out the data that's been logged and see what's happened, see if there's anything that you need to be really checking. So I think importantly, it's all about learning from what's happened. So hopefully this has given everyone an insight into the general gist of load monitoring systems and how they all go together. Now I'm going to hand back to Elliot.
Thank you, Tom. We now take this opportunity to discuss load cells in a real-life environment. We are going to discuss the 1975 World Tour, which started early 2019, which included West Point Arena in Exeter, which is only a stone's throw away from where Broadweigh products are designed and manufactured. Please remember, if you do have any questions, put them in the chat and we will answer them in the Q&A after this. So we are now joined with Simon Lawrence from the Rigging Co. Simon founded the Rigging Company in 2011, having worked as a tour rigger for many years with such artists as Arctic Monkeys, Disclosure, and now the 1975. He's in high regards amongst the rigging community. So Simon, hello and welcome.
Hello. Good morning.
So Simon, let's start off. Tell us a little bit about yourself, please.
Well, I guess, like most riggers, we often come into the discipline as failed members of other departments. I started as a lampy in those early days and was often asked, can we get a point in there? And when I was slim and fit and I used to climb, I would often go, yeah, let me have a look. And like a rat up a drain pipe, off I'd go, and that'd be it. And I realised quickly that was no good as a lampy, and I much preferred truss and motors, and the job move was done. Now, 32 years later, working in multiple aspects of the industry, live music touring, as well as small hotel rooms on corporate events. I'm the head rigger in 1975. Tour was postponed, obviously, due to COVID. We were in the middle of the world tour. And yeah, I suppose highlights of my career would have been working on things like Paralympics closing ceremonies, when I was involved as part of the production team for that. So that's kind of a nutshell of who I am and what I've been up to.
Excellent. Can you tell us a little bit more about the 1975 tour? So how long, how many venues?
Yeah, well, the tour started, I suppose, for us early 2019 with a UK run. We've been in planning and pre-production really since mid-2018. The tour was supposed to run until mid-2020 before starting the second album cycle and going around Airvision for a second time with another album. So then potentially another 12 to 18 months on top of that. In that we were probably with 100 plus of our own shows, headline shows, with festivals fitting on top of that. In terms of the band, I guess for them, their culmination was on the 1975 tour, would have been playing the headline slots main stage Reading and Leeds in 2019. They performed as headlines on lots of other stages through their career, and then they got the opportunity to obviously headline Reading and Leeds. For us, it was going to be a challenge because we were taking our full production in, and between us and the festival, trying to integrate that production was a bit of a challenge, but we succeeded.
So has there been much of a pause with obviously last year with what happened with the worldwide pandemic?
Yeah, I mean, we literally had just finished the UK leg on the 4th of March 2020. Gear was being packed up into sea containers to get ready to ship to America to head over there, and that was it. We were closed down. Gear got taken out of containers and the tour got put on hold. And band's still talking about going back out again, but at the minute they don't want to commit to anything until they feel it's safe to do so, as safe as it can be in a worldwide endemic that we've got going on now.
Yeah.
So next year again, we'll probably pick up.
Okay. So how many load cells are you using on a regular setup, say pre-tour, and when you are touring? Do you use the same amount of cells, from when pre-tour and when on tour?
Very slightly pre-tour and pre-production, our production rehearsal, should I say, we'll have more cells than we actually run on the tour. On the tour on a daily basis, we've only got 23 of the 4.75 ton Twistlink shackles. These are on our mother grids from which all our automation and video hang. Okay, cells are running into a Log 100 software, which is displayed on a large LCD display. So this allows easy viewing of the system from greater distances, meaning all departments can see any loads as they fly their elements. It just gives easy viewing locating our motor control location. In terms of Broadweigh kit that we run in, we have our own versions of the Broadweigh wireless warning module. It's exactly the same as yours component-wise, but we use slightly different strobes, and we have the ability to run it with battery backup. So we can pick the module up and walk it out to a location, and it'll sit there on batteries as opposed to being dedicated. So that's the only difference between our warning modules and the Broadweigh one.
I think that was pretty much the inspiration for ours. Really, it was I think I can't remember how long ago you did yours, but it was I remember seeing that and thinking that's a bloody good idea. So yeah.
I mean, I remember having conversations with you, Tom, back in probably late 2018 about how we increased our warning capabilities rather than using the relay modules, how we could utilize them to get more cells out there on it.
Yeah.
You're handing me a piece of code, in fact, back at 2019 at the West Point shows, and going, take this code, run it in the background, see what you think. And we redesigned our strobe beacons to work with the new code that you guys have come up with to produce the modules as we have them now.
So what roles are the load cells playing for your team? Well, not just your team, but the production company and anyone else on the tour?
Load cells are playing for the production company themselves. It's given us live monitoring of what's going on with the mother grids. The production our show isn't the heaviest out there by any means. We're only grossing in at 48 tons, which doesn't sound a lot, but when you compare it to some shows which are in excess of 100 tons from an arena show, we're relatively light. Our biggest concern is all our show weight is really, really densely packed into a relatively small 28-foot deep by 50-foot wide block right on the downstage edge. And our weight is very, very dynamic. Depending on what the show designer needs, on what we refer to on the tour as our cubes, which are some 2.4 meter square by 3.6 meter high video cubes, each of which weighs 1.2 tons. And we have 3 of those that track on automation go up and down, but also they will rotate. When they rotate, that moves the weight from our downstage of our mother grid, cross stage trusses, to our upstage mother grid, cross stage trusses. So the weight is physically shifting as the elements rotate around the center. We then have lighting trusses on there that are automated as well, that are moving up and down. And we have, again, what the tour refers to as a blade, which is, best way to describe it, it's a huge picture frame, which is 7 meters tall, 4 meters wide, and this can either sit horizontally above the stage, so the LED source is pointing down, or we can track it and rotate it and sit it vertically on the drum riser. And again, these elements are all interacting with each other. Elements are going up, elements are rotating, elements are tracking. And while that's happening, the weights are moving all throughout the roof. We've got clearance issues, so we need to know what's going on. At times, we've got about 100 millimeter clearance between some of the elements as they're actually performing. And a lot of those moves can happen in transitions between songs, so they happen in blackouts. So for us, we've got a lot going on, and we need to be able to see in real time, real world, what's happening with our loads in the roof to see if there's actually a problem occurring. Not only have we got the Broadweigh system running, all our automation hoists have their own load cells as well. So there's 22 automation hoists, 20 of those have got load cells on them directly linked into the Kinesis hoists. So if we see loads change, if we see load shifts, we've got parameters which will allow us to, in the shows, for the Kinesis system to take over and even stop moves. But in terms of the Broadweigh, it's actually seeing what's going on and helping us predict what's going on in the roof. I mean, we then squeeze more lighting trusses in and a drum riser, and then we dump another video wall upstage, 12 meters high by 9 meters wide. If that was flat, it'd be easy, but it's got returns in it, it's got bits to pull out. So it's all about knowing what's happening and being able to predict that information.
So do you believe that obviously knowing more now allows you to do more when it comes to touring productions?
Knowing more, certainly. 1975 for us, if we submit our figures, our peak figures of information to venues, they get very, very scared, because obviously we're looking at when this element is in this position, these motors are seeing these weights on them. If they start looking at our gross figures, what our hoist can predict, we start having issues where venues start saying we're starting to overload zones within the roof. So actually having the ability to say, well, now, and pictures, and what part of our advance is, I would send photographs to people. We're saying, well, in this position, this is what the cells are going to see. When we're in these looks, you're going to start seeing the weights change to here. So actually, you can see all the weights move into this location, and that helps us plan and predict where we're going to position the show within the building sometimes, because maybe we have to, as much as the audience dictates, we may have to move the show around to be able to manipulate it around the structure in the roof or the loading zones within the roof.
Yeah. So what kind of performance have you seen from the Broadweigh systems, say in terms of signal quality or battery life?
Signal qualities, battery lives can be really, really good. For ourselves, I'm not too worried about battery lives on a show. On a project that's running 18 months. Environmentally, it's not so great. Yeah, we're swapping batteries out, but we can run a high transmission rate of the cells, which gives us a really, really stable platform for us to work on. The spectrum analyzer in the toolkit that comes standard with Broadweigh is really good, because in the morning we can walk into a venue, we can do a quick scan of the room as to what's going on that 2.4 gigahertz range and find out if it's really noisy in the areas we were working in previous shows. If it is, we have the ability to, by using the groups, we can move all our cells to a different group within that bandwidth. Having the ability to make minor adjustments with sample rates creates a very stable platform for us. We've been very successful.
So what sort of sample rate are you going at generally then?
We're running about 300 milliseconds.
300, so 3 times a second.
3 times a second, yeah.
Okay. So I think you'd probably get 24 hours a day. I think you'd still get probably a month's battery life out of that.
Yeah,
constant.
yeah.
So and yeah, so it's still not the end. It's not like you're having to change them every venue, is it?
No. That's, as you say, we're probably still getting 28 days, I think, battery life. But it gives us that ability with that sample rate. It's great. I mean, we've had real success by running those kind of sample rates with 20,000 people coming into an arena. When they walk in, all the phones are hunting to jump on that free Wi-Fi within the venue. All the phones are quite happily sitting there hunting away on Bluetooth, trying to find all that Bluetooth and looking for all the things that the Bluetooth is looking for that isn't there. And we're able to push through and literally quite happily watch the cells all the way through and have live monitoring of the show for the entire performance. Yeah,
pairing to the Bluetooth flip-flops, I think, yeah.
Yeah, that's it. And also noise from the LED walls, but we won't touch on that subject today. So you were an early adopter of the Twistlinks. So how do these help you?
As Twistlinks, yes, totally love them. I remember badgering Kelly for them quite a lot, saying when are these coming out, when they're coming out. And as soon as they were available, we had a batch of cells going in there to get converted over to Twistlinks. Touring is very, very time sensitive, which is where we do most of our work. In one city today, do a show, move out, as people know, next city tomorrow. So you try and do things as effective and to save time as possible. So every minute counts for us. We've only got 23 cells on the tour, but also the Twistlink saves us height as well. And with a show, and this is going to sound really crazy, we've got a 20-meter hook height on our show. Not many venues in the UK and around the world can give us that hook height. So any time we're sacrificing against it, it puts more work, more effort into other departments. So even if I put a pairing in there or a master link, we're probably now talking 200 mil between the load cell connection and the truss pickup. Whereas with a Twistlink, it's 70 mil. So it's a saving, and it saves time with other departments having to do work for us. Because the Twistlink is permanently attached and incorporated, it sits in its transit case, standard transit case, really, really nice. You can pull it out, clip it onto the motor, and away you go. If we were to put and because the transit case are all custom foam shaped, they transport nicely, as opposed to putting putting a master link on it, and it's sitting and rattling around in the bottom of the flight case. Potential for damage is there. So you would end up taking the pair link or the master link off and adding it on a daily basis. Well, if you said that took you a minute to do, to take it out, take the pin out, put it all back together again, with 23, not a lot of time, but that's another 23 minutes of time, which when you've got a stage manager or a production manager breathing down your neck, and for our show in particular, because it's on mother grids, if those mother grids are not in the air, other departments are not working. And that could impact financially in terms of a huge overtime bill for stagehands as the day goes on. So if rigging and dragging the feet and are not getting things going in the air, particularly because of something as simple as the Twistlink, and that's just my personal opinion, you're going to get someone who's going to be asking why and what is out there that allows us to speed it up.
Yeah. So looking to the future, what's your hopes for the industry in terms of load cells and sensors in general?
What I would like to see in the industry is whenever a hoist is hung, a load cell is included in the system. That's my ultimate goal. That's where I would like to be, and that's how I would like it. People are aware of them, and heaven forbid there was an incident or even worse, loss of life, then people are going to ask the questions, why weren't you using something to monitor those loads? How could you let this go? And if you to stand there in a court of law, in the eyes of the law, and turn around and say, well, it costs money and we didn't use them, it's not an excuse. It's going to take time, like anything, trying to convince people that they need to spend money on something that it isn't a big fancy video wall. It's not a brand new line array of speakers. Something that people say when you're talking about what to them just is a shackle. It will take time to make them realise that those kind of things they're going to have to be paid for and change the code. But it'll come. A few years, but we'll get there in the end.
Excellent. Well, thank you very much, Simon, for your time today.
Okay.
So we'll be back in 1 minute, and we're going to answer everybody's Q&A. So again, thanks very much, Simon.
Thank you.
Okay, thank you for sticking around. We have some Q&As to go through now. We have some pre-submitted questions and some questions that have been asked. So we shall fire away with the first one, which is, can we talk about the relative merits of wired versus a wireless system? So here at Broadweigh, fundamentally, we are specialists in wireless telemetry, which is which comes from the Manchester Court side of Broadweigh. Hence why currently all of our shackles are wireless. It's what we specialize in, and we see more benefits in having a wire system, so you don't have all the wires going everywhere. Hence why we have progressively continued to produce wireless shackles. Tom, have you anything you want to add to that?
Yeah, it's mainly on ease of use, really. It's a much simpler thing to be able to use. You don't have to affect everyone else anywhere near as much when you're putting a wireless shackle into the system. You don't then have to run a cable all the way along down your cable loom and everything. So it makes life a lot simpler. There's actually marginally less cost as well, because you're not having to pay for your cables. So that's the general plus points of the wireless. Wired people quite like, because there's a sort of perception that it's a little bit more secure or stable rather. But you do still have the problem that if you lose a link in the system, especially with the digital ones, everything downstream of that is then lost. So there's problems with both, really. I mean, you could get interference on wireless as well. So, but yeah, generally, I would say that wireless is the simplest, easiest option.
Excellent. Simon, have you used both wired and wireless systems before?
Yeah, we run on jobs with you both wireless and wireless. Speed and efficiency for me would be in getting it in the morning. Wireless system is great. It comes out, it hangs very, very quick. For us, if it shows critical data, and I know you can still lose cables, you can still lose links. If it's show critical and we don't want the risk of having data drop out on something, we will always go down a wireless system. But predominantly 95% of the time for us, we're going to be running a wireless system.
Thank you. Next question from Anonymous is a question for Simon. What has been your career highlights to date?
I suppose career highlight, for me, a couple of shows stand out, and that's working on both Paralympics closing ceremony and the Help for Heroes fundraiser event at Twickenham a few years back. Both of them, not necessarily on a rigging, there were challenges in both, but it's as a job, just working around people that made you realise that for us, what we consider difficulties, actually for them is normal life for them, and they make you look humble and make you, you realise that you haven't got problems in the world. Everything can be overcome. You just got to put your mind to it, and you can relate that to business as well.
Brilliant. I have a couple of safety factor questions, so I'll ask them both together, which is, what is a recommended safety factor for a load cell? Also, what is the minimum and ideal safety factor a load cell should conform to in the UK? And does this change when operating in the EU, US, especially Germany?
So I don't think that there are any standards or legislation specific to load cells. So you probably have to look more towards something like the Machinery Directive in Europe, or supply of machinery in the UK, which is basically the same thing. And in that, for things like shackles, the recommendation there is about 4:1. In the BSEN 13889, which is the shackle standard, the safety factor is 5:1. But that's all on general use. So it's those are the sort of minimums, I think. And then people talk about when you're in more critical systems. So if you're working out at sea, if you're lifting performers and things like that, there's people talk about doubling your safety factor. People talk about an 8:1 or a 10:1 safety factor. It basically depends on your risk assessment and things like that. But the base safety factor would generally be about 5:1, I would say.
Okay. I have a question here for Simon. Simon, you said that you need 80 plus load cells in a rehearsal and only 23 on tour. Why is that?
Reason why we run a lot more in rehearsals, one is producing load reports, which we're going to submit with our advance. For every venue we're going into, we need to submit a rigging plot, which has got weights, detailing what's going on, locations of where those need to be. By using 80 or 85 cells in rehearsals, we can create that and generate that report. Reports have got serial numbers of the cells log tracked into them. It's got test calibration certificates of the cells. So it's all information basically to prove what we're telling and make people understand. Problem we had on one of the big problems we had on the show is if we submitted our report off of just peak maximum load grab data off the cell report, the show suddenly looked really, really heavy in lots of places. But actually, we were only seeing those loads in certain amounts of time. So actually, for us, with our report, what we were doing was taking pictures of the show and saying, in this show position and this show look, this is the regions you're going to see on this particular part of the mower grid. Then we change the automation looks, change the show positions, weights would change around in the roof, and then we could submit a photo. And it just helped people understand the venues, the venue riggers, people who were doing the analysis on the venues, understood how our loads were moving around in the roof, which is how they then base information that we need to tell us how to work with and how we're going to get that load into the roof. It might not just be as simple as, well, we can hang it in that bay. We may have to hang it across multiple bays in the roof, which then will affect our trim heights if we were bridling across situations. So it's all part of our advantage, the reason why we need large number of cells to weigh the show in rehearsals as opposed to what we actually need in real time.
Okay. This leads straight into another question. So things change whilst you're on tour, and if you need to monitor another point, what do you do?
For us, what we did literally towards the end of the run, just prior to closing down with COVID, we added some of the Bluetooth cells into our touring package. Really quick, really easy to set up. We didn't need to build them in on a daily basis. You didn't need to be in there. But if we make changes, and I'll use an example of the PA, you spoke to the PA guys, the systems techs, and they've decided they're going to hang 10 boxes in a venue that morning. They get in there, they suddenly find we've sold more tickets, things have changed, and you're having to say to the venue rigger on the guy or the buildings, whoever's in charge of rigging in that building, oh, weights are actually going to increase. Sometimes they get a little bit, because they've advanced it, they've signed off to something, they'll get a little bit. So what we can do, we can add extra cells in, we can add load cells in, you can see the weights, and we can actually prove to you what we're saying is going to be the changes, it's going to happen. So the simplicity of the Bluetooth system was great. They could hang in there, we didn't need live monitoring, it was purely data to be taken at the start of the day. So that's how we're going to start addressing last minute changes into the rig.
Excellent, thank you. We've had another question come in. Can you speak more about the merits of an alarm-based system versus an EStop stop-all system, particularly in terms of the new EN 17206 regulations?
Well, first of all, I unfortunately haven't managed to get that standard yet. So that is on the list of things to do. So I can't make a comment in terms of the 17206, but generally I think the alarm based and the EStop, the difference is well, it's personal preference and risk assessment again. So the alarm based system still involves having someone make a decision. So you've got your alarm going off and someone then has to decide, do I stop? Do I keep going? Which in some cases is the right thing. And you need to sometimes you need to have a physical person making that decision. Other times with a sort of an auto EStop, then you don't, it needs to just happen. It's too system critical that it just needs to stop. The other thing, though, to bear in mind when you have got an automatic stopping system is, how do you unstop it? So how do you make it safe again so that it all starts to work again? So that it's all part of the that risk assessment and the design of the system, and making sure that those things all work together for the particular thing that you're doing at that moment in time.
Thank you, Tom. Question here for Simon. Do you use the visualization in the Log 100 software, and is it more beneficial?
Yes, we do. On a large scale job, yes, we'll spend quite a bit of time, and it is quite slow process building the visualizations. For us, we'll submit on the 1975. We have multiple pages of information. So we would import a rigging plot into it, put assignments to it, location, so people can visually see what the hoist was, what its location is within the rig, and then the ability to look at different areas within it with having a screen full of information, so you can obviously like zoom in on locations and pull up the relevant information across. Visualization is great. It is dependent on the right cell being hung in the right location for the day. If someone hangs, I guess with anything, if someone hangs that cell in the wrong place and you're looking at information, and you could relate it back to the question about warnings. If a warning's going off, and what you're seeing on the visualization is where you believe a problem to be, then actually it may be misleading if someone's put it in the right place. So you've got to, if you're going to use it, you've got to know that that cell is in the right place all the time.
Thank you. We've had another question just come in. Can somebody get into the transmissions? Can it be hacked? Considering it's wireless, no, you can't. You need to know the ID of the shackle, and also you can make group keys, adding another layer of security. So in short, no, not unless you have the information of the shackle and your own software. Got another question here. This one can be for you, Tom. What is that accuracy a percentage of the load or the capacity of the load cell?
So in terms of general sort of spec sheets, that depends. So I'd say probably the majority of general load cell manufacturers will quote their accuracy as a percentage in terms of the full scale. We are slightly different, which makes it a little bit, so percentage of full scale is really easy. So plus or minus 1% of 3.25 ton is plus or minus 32.5 kilos, and that's at any point in the range of the cell. We do it slightly differently, so that we say it's plus or minus 1% or 25 kilos of the currently displayed reading. So that means that at the lower levels, you're looking at plus or minus 25 kilos up to sort of 2.5 tons. And then after that, it starts to get a slightly bigger gap in the potential accuracy.
Thank you. Okay, we've got time for a couple more questions. We've got another one here is, with the Bluetooth system, how many people can see the weight data? As many systems as receivers. If you've got multiple phones, iOS or Android device set up reading the data, then you can have multiple.
It's theoretically almost infinite.
Exactly.
It's probably not in practice really infinite, but
yeah.
If you start to get people in the way,
more than you'd need.
Yeah, it's basically it's a broadcast protocol, so there's no two-way communication. So you're just receiving the data, and you're not sending anything back to the cells. So yeah, it's very simple and easy to just fire up another mobile phone that knows knows all the right codes to access the particular shackle. But yeah.
A couple more. We've got one here from Mike. When should load cells be calibrated?
Our recommendation is that one of the things, first of all, I think it's like an MOT. It's the point at which the calibration is right is the point at which it's in the factory being calibrated. After that, who knows what can happen? You could the shackle could get hit by something. You could shock load it in much the same way as your car could go down a pothole and break your shocks. And your MOT is still valid for the next 11 months, but actually it's not working properly anymore. So there's probably an argument for every time you use it to just have a bit of a reality check on it. You don't necessarily have to calibrate it every time, definitely, but there should be I think that as a bare minimum, you need to be doing a check with a known load at least every 12 months, and you should be getting it recalibrated or calibration checked back at the manufacturer at least every 2 years.
Thank you, Tom. We have another question in. Are your load cells compatible with Kinesis load cells?
It depends on what you mean by compatible. They'll coexist. They won't interfere with each other.
Yeah. I mean, Kinesis are a wired system, and Broadweigh is wireless.
Yeah.
So they will communicate completely differently. So like
Yeah.
Tom says, yeah, they can coexist on the same rig, but you'd have two different ways of reading that data.
Exactly. Yeah.
And we have time for one more question, which is, are there any plans to make the desktop software Mac compatible? We have this question asked a lot. Currently, the current version of Toolkit and Log 100 will not be Mac compatible. And there is the potential in the future, if there is a new software design, that it might be Mac compatible, but as on the whole at the minute it's a no. I personally am a Mac user and I have very good results using Parallels and running Log 100 and Toolkit with Parallels. And I think that concludes today. We've had one more question come in. We've got time. Yeah, we'll just quickly. How would you rate your system compared to Ron's system?
I have never used Ron's system, unfortunately, so I can't do a direct comparison.
No, I have never been hands-on with a Ron system either.
No, you've kind of got all of us on that question.
Yeah. But thank you for the question. And I think that concludes us today. So thank you everybody for tuning in and listening in to Tom and Simon. And we hope we'll see you again in the future. Thank you very much.
Thank you.
Thank you.